We'll focus exclusively on the hurricane threat here today. We do it from both sort of a forward-looking perspective, doing modeling and things like that, but also looking into the past of both historic storms as well as prehistoric storms that we can actually get from geologic evidence. So first I'll cover a little bit what I'm talking about. I'm sure most of you have been watching the Weather Channel today, but tropical cyclone forms in the tropics or subtropics. Its basic fuel is the warm sea surface temperature, so it's pretty different from an extratropical system that's getting its power, its energy from frontal systems, or the meeting of warm and cold air masses. This is something that's actually spawned over warm sea surface temperatures, and that's why there's such a concern about global warming and why sea surface temperature increases might increase the intensity and perhaps frequency of tropical cyclones. So here's where they occur. This is a snapshot of over the last few decades. You can see that mostly it's in the northern hemisphere, but you do see some in the western South Pacific and the Indian Ocean. The biggest hotspot is in the western North Pacific, but here in the Atlantic we also get our fair share of them. And I'll talk a little bit about categories, and I'm sure most of you have sort of heard these before. We often talk about them in terms of Saffir-Simpson category 1 through 5. Right now we have a category 4 bearing down on the Bahamas, and this is the wind speeds. And so for a category 1, we're looking at something that has 74 to 95 mile an hour winds, and then on up to greater than 155 miles per hour, which would be a cat 5.
The thing on the left advances.
Technology.
Yeah.
There we go. One thing the Saffir-Simpson scale doesn't really capture, though, and something we've become aware of in the last decade or so, is that they come in very different sizes, right? We learned that in Sandy. This is actually an old slide. Before Sandy, Ike had been the largest hurricane in the Atlantic Basin. But you can see you can get them quite small, only a few tens of kilometers across. So very different scale, and obviously very different energy. So the Saffir-Simpson scale doesn't quite capture all of the parameters that sort of matter. This is a summary plot of what we think we know about tropical cyclone activity since record keeping really took off in sort of the mid part of the 19th century. We have a pretty good sense for the biggest storms prior to that, but it wasn't until we had enough ships out on the ocean basically encountering these storms that we feel like we have a pretty good idea of the total numbers. Now, one of the things that's apparent in this, and so this is the major hurricanes are in red here, and this is just a histogram, and it's sort of stacked on each other. But you see this sort of upward trend here, and this was an early concern. Oh my gosh, there's this increase in tropical cyclone activity. But there's also a pretty big observational bias potentially worked into this, right? Where up here we have satellites and we're not missing a single storm. Whereas back here we're dealing with ships that happen to encounter the storms and survive and to tell the tale sort of thing. And so part of this could be an artifact of that observational bias. Some of the theoretical work, though, based on that notion that these tropical cyclones are basically getting their fuel from the sea surface, have suggested that we should see more intense and more frequent hurricanes during in intervals where the sea surface temperature in the areas where they form are warmer. This is another observational data set. The blue here is the sea surface temperatures over the last several decades in the deep tropics of the Atlantic. And this red here is sort of an integration of the total energy expended by hurricanes. So rather than a count, how many hurricanes do we have? It's sort of how long did they live, how strong were they, sort of integrates all that. And you can see there's a pretty strong relationship between changes in sea surface temperature and tropical cyclones over this interval, which sort of supports that notion that sea surface temperatures are important. And so we've sort of gone out, we're trying to project sort of future changes, and this is actually based on a series of models that formed the basis of the IPCC report several years ago, and I'll show a more up-to-date version of this next. But what we did was basically to say, okay, in the best case scenario out of these models, what might we expect? And so the model that basically had the fewest number of storms, the least amount of activity versus the worst compared to modern. And this is going on actually 200 years, so it's not something we're predicting for next decade or the decade after that. It's sort of a very long time scale. But at 2200 AD, we're looking at sort of a doubling of activity in the best case scenario and close to a tripling of activity in the worst case scenario. And now there's a new version of this that came out recently, where they're using the next generation of the models. And this is sort of a time series looking at the frequency of events. And again, this is largely driven by the warming sea surface temperatures. You can see that the annual frequency of events is going up considerably, and this is over the next several decades out to 2100. There's a lot of spatial variability though too. So here's a map of how that sort of maps out, and you see that the big loser here is the western North Pacific. So if you're thinking about buying coastal property there, you might think twice. But there is sort of an increase here in the Atlantic as well that we might want to pay attention to. Now this is one modeling exercise. There are several others that suggest there's only an increase in the frequency of the most intense events and not the overall frequency. And so there's still quite a bit of inconsistency with the model results. But nonetheless, there are several of these that are pointing toward potentially more activity. On top of all this, we know that sea level is rising, right? So there's no debate about this. We can actually measure it, and we're actually measuring it all over the planet with tide gauges. We've actually been able to go back in time again with these geological proxies as well, and go back several millennia, and I'll show a little bit of that in a minute. But this is again a figure out of the more recent IPCC report. And so the long-term trend in sea level in the early part of the historic interval was pretty flat. And it wasn't until basically the later part of the 19th century that we see this uptick in the rate of sea level rise. And then that brings us to here, and these are the projections for the future that was in that IPCC report. All of these others are other projections that were done by independent scientists, not necessarily associated with the IPCC. And you can see there's a fairly big range here, and much depends on the emission pathway that we choose, whether we do anything about putting CO2 and methane into the atmosphere or not. But the upper end here, we're basically looking at something like a meter, which would be about 3 feet of sea level, all the way up to maybe 1.5 meters when you're looking there, close to 5 feet of sea level rise. Again, by 2100.
Jeff, what's different about the yellow bar? What were their parameters? Why are they
so that was the earlier IPCC report, 2007, I believe. And there was a lot of criticism about that, and then many of these papers that followed and largely it was that they didn't know the answer about how much water was going to come off the West Antarctic ice sheet in Greenland, and so they just left it out. So they didn't have a good number, and so really this is largely just based on the thermal expansion they expected in the ocean as it warmed. It wasn't taking into account the actual mass of water that might melt off these ice sheets. Whereas now these attempts and this try to incorporate some of those estimates. Did you have a question?
Yeah, the sea level rise is not equal around the world.
No, it isn't. And we're going to see a figure on that very shortly. The other thing I wanted to talk about is obviously over the same time interval, there's people on the landscape, and we're having an awful big effect as well. Here's the population of Barnstable County going back to 1900, and you can see this big exponential increase in our population. We've hit sort of a flat spot. I don't know whether that's just economics or whether we've sort of reached our potential in terms of people in the Cape, but nonetheless, over this interval, and largely in the later half of the 20th century, we've had a huge increase in the population on the Cape, and that's a trend that's all over the place. It's one of the reasons why Sandy was such a big event in New Jersey, is because of this huge population boom. The last hurricane that hit New Jersey was in 1821, and the only thing that was on barrier islands then were a few fishing shacks. Now we have Atlantic City, right? So just to give you a snapshot, this is what, it didn't come out very well but this is a map of Falmouth in 1886, and this is a photograph of it today. You see the only places we really had houses here were on Shore Street, Main Street, along the main roads, and none of this was really developed. And of course today, everywhere there's development. So along those lines, if you look at, this is some work that some colleagues of mine did. So if you look at the damage that's occurred over the 20th century related to tropical cyclones, you see this big sort of increase that sort of mirrors that population gain. And initially when this came out, people were like, oh my gosh, this matches that earlier figure where there's increasing hurricane activity. Hurricanes are getting stronger and causing more damage. But it turns out it's really that other figure, it's the population growth that's causing this. It's not necessarily that there's more hurricanes, it's that there's more of us and more of our stuff in harm's way. And so what they did here is to try to account for that. And so basically they're asking the question, what if these earlier hurricane events were to hit today, given the population that we have and the wealth, basically, that we put at the coastline? And they come up with a very different answer. This is what it would look like. And so in effect, they're sort of asking, you know, if the 1926 Miami hurricane were to hit today, what would the damage be? And in 1926, there wasn't much of anything to Miami. Of course, now it's a huge metropolitan area and would be sort of a $150 billion sort of loss. So it's sort of a complex, it's not just what we're doing to climate and what climate's doing to us. We're also sort of a player here, and we're sort of putting our stuff in harm's way. And so that's, I think, some important context to think about. So here are some of the bigger events, and we'll talk a little bit in a minute about the 1938 New England event. So this is effectively saying that if that 38 hurricane were to come back and hit today, we'd be looking at something like a $40 or $45 billion loss. And then obviously these are the more recent ones that we all remember, from Katrina to Sandy. Okay, so I'm going to get to sort of the data now. This is the tide gauge record from Woods Hole. So NOAA put out a gauge and has been recording tide movements there since the 30s. And we've basically measured most of the extreme events since that time. And this is how that plays out. Here's the time scale here, from the 1930s up to modern. You know, we have lots of high water events. These are the monthly high water events since the onset of the record, I think roughly 1930. Here's the 1938 hurricane. So this is meters of storm surge above mean high water, basically. And so you're looking at about 2.5 meters. We had a hurricane in 1944, which, you know, was about 1.5 meters, 1.7 meters, something like that. Hurricane Carol was sort of comparable to 1938. Hurricane Donna in 1960. Many of you probably remember Bob in 1991. Irene is here. Sandy is here. So fairly modest events relative to some of these larger events earlier in the record. The star is actually what we would have likely gotten had Sandy hit us instead of New York. So if Sandy hadn't taken that really odd recurve into New Jersey and just come straight up the coast, it would have given us a little bit more than it actually gave us, but not quite as much as Bob. So it wouldn't have been quite as bad as Bob.
Where is that tide gauge?
It's right there on the Hui Pier, right downtown, or right in the village there. You can't access it. You know, if you're going down Water Street there's our main lab there, and the pier that goes up. It's on that pier. And then these are some estimates that we've done for earlier historic events that predate the tide gauge record. And some of the big ones are 1815, which we'll talk about in a minute, and 1635 is probably the biggest one. Okay, so here are those sea level measurements. And so we've actually been able to reconstruct how sea level has changed at a whole variety of locations. And as was pointed out, it varies, right? And so the green here is what sea level has done in New Jersey over the last 2,000 years or so. North Carolina is in the red, Connecticut is in the orange, Florida is in the blue. And you see, all sea level is really local, because it turns out the land is actually doing quite a bit. It's not just what the sea level is doing, but the land is actually moving as well. I don't have Massachusetts or Cape Cod listed here, but we'd be pretty close to the Connecticut curve here. And the reason they're different is that we're still sort of responding from when the ice sheet was here 21,000 years ago. Right? So the ice sheet is basically what forms Cape Cod. It pushes out all the debris that makes the Cape and the islands, retreats. It's had so much mass that it actually pushed the crust of the Earth down, displaced this sort of plastic, more fluid mantle material further out, and then the ice sheet went away. But it turned out that the relaxation time on that is really slow. And so Hudson Bay is actually uplifting like crazy. Sea level is actually falling there quite rapidly. It's because they're stealing our mantle material. The mantle is actually moving from where we are to Hudson Bay, and so we're actually subsiding. So in addition to sort of what the global estimates of sea level change might be, we've got to sort of add on this extra bit of subsidence that's going on here. And it turns out New Jersey is subsiding even more. So let's see. So here is an attempt, we basically have corrected for all those land movements to try to get at a projection of what the global sea level has been from records like those from all over the world. And basically, as you go back to about 1500 AD, sea level was pretty flat. And it wasn't until, again, that later part of the 19th century where sea level began to rise. And the current rate of rise is actually higher than anything we've experienced in about the last 6,000 years since that ice sheet completely melted away. And then these are all projections which fed into that earlier plot that I showed you about. There are different pathways that we might take in terms of our emissions. Obviously, we haven't done a very good job in sort of mitigating carbon emissions, and so we're still sort of at the high end here. And so until we figure that out, we're much more likely to be on the upper bound here than the lower bound. But again, you're probably thinking about something in the order of 2 to 3 feet, and perhaps even more of sea level rise in the next 100 years or so. Okay.
Does the
Sir.
coastal erosion cause any significant effect on our sinking?
No, because it's mostly just moving the sediment around, right? You might lose it from here, but it goes over there. So the scale of that is very different from this, sort of ice sheet scale. So let's talk a little bit about the hurricane history. So this is most of the events that have hit the region since Europeans arrived and started writing things down. The reds are really intense storms, so they're roughly category 3 in intensity. The blacks are category 1, category 2 in intensity. Here's Hurricane Bob, which many of you probably remember, went right over Block Island and made landfall near Newport. Here's Sandy, obviously, it's really the sort of anomaly here. You can see it's a pretty odd track. It hasn't really been something we've experienced over the historic interval. A couple of storms that I'll talk about, some of the big ones that I showed in that tide gauge record are 1635, 1815, and 1938 here. So here's 1635. We happen to know as much about it. Let me go back actually, because you can see the track actually passes between Plymouth and Boston, the only place there's actually Europeans in the landscape writing things down at that stage. So from our perspective, sort of looking back, it's a really fortuitous track. So now we have quite a bit of information on the characteristics of the storm. And here's just a couple of examples from the two governors that they were writing in their journals. Now the tide rose in Narragansett 14 feet higher than ordinary, drowning 8 Indians flying from their wigwams. Mighty wind that neither English or Indians had saw that caused the sea to swell to the south wind of this place. And this is Bradford talking, so he's in Plymouth. So we're presuming that he's talking about Buzzards Bay to the south of Plymouth. Rose up 20 feet right up and down and made many of the Indians climb into the trees for safety. And this is sort of telling too, and it blew down many hundreds of thousands of trees, turning up the stronger by the roots and breaking the higher pine trees off in the middle. So we're actually been able to there was enough information provided by all these documentary sources to actually try to hindcast model what this event must have been like. And this is a slosh model run. Slosh is a storm surge model that the National Oceanic and Atmospheric Administration uses operationally. But we're actually able to use it in sort of a hindcast mode. And so it's sort of a similar track to Bob, where it's sort of making landfall over here near Narragansett, goes up between Plymouth and Boston. And this is sort of this last slide here is the maximum water level achieved. And you can see that, just like we basically tuned this to those observations, so south of Plymouth in Buzzards Bay, you're getting 20 feet of storm surge. But and you've got this focusing. So one of the things that makes Buzzards Bay and Narragansett Bay very vulnerable is that there's these south-facing funnel-shaped embayments, and this big surge comes up, and there's no place to go as this thing narrows, and you get an accentuation of the surge in here. So it's pretty common. We saw this in Bob as well, and I'll show. I think it might be the next slide actually of what Bob looked like. But even we had 20 feet of storm surge here, but even out here we're still looking at 13 or 14 feet of storm surge from this particular event. So I think I put Bob up here. Yeah, so here's Bob. And Bob, this is on the same scale. And we had about 12 or 13 feet of storm surge up at the head of Buzzards Bay in Bob. Bob was a Cat 2 storm at landfall. That 1635 was probably a Category 3, similar to 1938, except for us it was a much worse event because it made landfall much closer to us. In 1938, much of the damage was in Rhode Island, Long Island. We got a pretty big surge here, but we were sort of right on the cusp, right on the edge of that particular event. So, one of the things that we're able to do actually with this now is that we've been able to hindcast all these historic hurricane events. And basically use the slosh model to say, okay, what are the parameters that would be required to give the observational record that we have. And so what we basically have these hindcasts would give us surge values for all these different events, and now we can say, okay, what would happen, regardless of climate change, right? Because there is quite a bit of uncertainty, although I think we're sort of moving in the direction of there's probably going to be an increase in activity, but there's still lots of uncertainty. But what if we just had to deal with what we've already had to deal with? What if something like the 1635 hurricane came back today? What would those impacts be like? So here's downtown Falmouth. Some of you probably recognize it. Here's Main Street here. This is plotting the surge that we'd expect from a 1635 like event on the town of Falmouth. And you can see, and that's the blue, right? And that's at modern sea level. So if this were to hit next week, this is the sort of level of surge we'd expect. You can see it sort of just makes it up to Main Street here and basically floods Town Hall. It also comes up here and floods the intersection by Friendly's. That's Friendly's right there. Starbucks is right next to it. That's Staples. So that intersection is basically underwater during that event. And for you Walmart fans, that's Walmart, that red thing there. So basically Walmart becomes an island. Yeah. You might want to go to the roof of Walmart if you happen to be there when this sort of thing happens. But one of the things that I think is that this sort of approach can do is to sort of, okay, what might we expect in the future as well? And so we've run this same storm, not just at modern sea level, but what happens when we get a half a meter of sea level rise, a meter of sea level rise, or perhaps the worst case scenario, about 1.5 meters of sea level rise. And you can see, obviously it gets progressively worse. And you don't quite make it, but if we were to get 1.5 meters of sea level rise and get an event like this, you nearly turn downtown Falmouth into an island. And even at just modern sea level, you turn Falmouth Heights into an island. And I think this is sort of our worst case scenario in terms of what we know from the historic record. We've had many other hurricane events that have been not nearly as bad as this, and so at least in my head, this is sort of the thing that keeps me up at night if we get something like this. But obviously it's been 400 years and it's only happened once, so it's not all doom and gloom here, but it might be something that we need to be prepared for. So one of the other things that is often missed in those sorts of plots, right, is that it tells you who's wet and who's dry, right? It doesn't actually tell you how much water you get and how fast you get it, right? And so this is the actual hydrograph that you'd expect in downtown Falmouth, and basically in Falmouth Harbor, and up in Buzzards Bay and Bourne from this particular event. And I didn't show it earlier, but we're talking about Sandy. Sandy was sort of unusual for a couple of reasons. One, it took that really odd track, but it was also moving really slowly for a storm at this latitude. Usually storms come up the eastern seaboard and accelerate. So Sandy was sort of like an all-day event, right? The surge actually started early in the morning, and it actually was really bad luck that actually the peak of the storm hit at high tide, which is what caused much of that flooding. Much more typical is something like this, where the event happens and it's over in a few hours, right? So here in Falmouth, you get a surge that's roughly 10 feet or so, much closer to 20 feet in Bourne, and again, this is basically happening in just a couple of hours, and basically in 3 hours, the event's basically over. So just to go back to a couple of other historic examples that aren't quite as bad, but would certainly wreak some havoc. Here's what would happen if that 1815 hurricane would have returned today, with the amount of sea level rise that's occurred since then. And again, the blue is modern sea level. The green is what you'd expect if you had a half a meter of sea level rise. Yellow is 1 meter. Red is 1.5 meters of sea level rise. And this is pretty similar to the 1938 event as well. And so there's actually a painting that was done after the 1815 hurricane of downtown Providence underwater. This is obviously way before they put the hurricane barrier in the 20th century. And then there's this great historic So before we put the canal in, obviously, there's this historic account of the storm surge actually coming up in Buzzards Bay and coming within 15 inches of actually breaching that isthmus and creating an island effectively. So, and if you look at the old topo charts, that's about 20-25 feet where that was. So the surge came pretty close to breaching it. Okay, so here's the same thing for 1938, pretty similar. So you're basically seeing all sorts of flooding along the shore. Doesn't quite make it nearly as far as the 1635. Doesn't quite make it to Town Hall. I guess it's lapping at Town Hall's door there. This intersection is free, at least in the modern sea level scenario, and also you don't quite get to Walmart for what it's worth. And then here's Bob. So most of you probably remember that. You know, we had quite a bit of flooding down by Salt Pond, up into Sitter's Pond here, and along the coast. But it didn't really penetrate that far inland. But obviously, as sea level rises, even a Bob-like event that we see much more frequently would cause substantial flooding along the coast. So I'm going to just briefly talk about what we learned from some of the sediment records. Here's us coring in a coastal pond. This is actually Oyster Pond in Woods Hole. And so we use these sediment cores to actually find, there's a sediment that's accumulating in the bottom of these ponds. Turns out when hurricanes hit and that storm surge comes up over the coast, it transports the beach sand into the pond, and we see these sand layers that sort of mark their occurrence, right? So we're actually able to reconstruct them through time. And I don't want to spend a lot of time here, but this is the last 2,000 years of the record from Salt Pond here. And one of the things that's interesting is that there's lots of variability. It turns out between 1400 and about 1675 AD, it's quite active, including that 1635 event. And then much of the first millennium AD was also quite active. And it turns out both of these are associated with warm sea surface temperature events. I'm going to skip that because it's just, skip that too. So this is just going to focus in on the that 1400 to 1675 interval where there's lots of these event beds going on, including 1635. It turns out there's some climatological things going on here. Not only this is an odd interval where we see a sort of a change in what we call the intertropical convergence zone moving southward, but we also see this big warm sea surface temperature anomaly along the eastern coast of the U.S. And so that's likely fueling these sorts of events that are basically forming as Joaquin has, sort of up here north of the Bahamas, and feeding off that warmer sea surface temperature and moving up. So, just to give a bit of a summary, we know from the geologic record as well as the historic record that there's quite a bit of natural variability in the system. Right, we know there's lots, there's intervals where it's very active, intervals where it's pretty quiescent, and that's even true of the 20th century. We had the middle part of the 20th century, which is, we had 1938, we had 1944, we had 1954, we had 1960, and then largely we didn't see anything until Gloria in 85, and that was mostly a New York event, and then it was Bob, right? But even on these much longer time scales, we see that as well. So sort of makes it a pretty complex issue to try to tease out what humans might be responsible in terms of climate change and what the natural system is doing. Nonetheless, there is this variability, and I think it's something we need to be prepared for, regardless of who's at fault, whether it's us or whether it's just something the climate system does on its own. So looking out, the theory tells us we should probably see more intense hurricanes. The data suggests a really tight link both in the paleo record but also in the modern record between sea surface temperatures and hurricane activity. It's likely that we would see increases in activity in the future. That being said, it's clear in that modeling exercise that not everybody's a winner and not everybody's a loser. Some areas might see a decrease in activity where others might see an increase. Regardless of where you stand on global warming and what happens in terms of global warming and tropical cyclone activity, sea level's rising, it's going to continue to rise, and so even if we still have the same hurricane climate we've always had, there's going to be an increasing risk. You saw those colors sort of moving up that map there. Even if we just get the same old hurricanes that we've always been getting, our situation is getting worse because sea level is continuing to rise. I think that's it. I'm going to leave you with Joaquin, for better or worse. But you can get more information here at our website. We're trying to make an actual viewer to actually be able to zoom in on these sorts of basically asks the question, what would happen if the 1635 came back today to my house, sort of thing, you could view your house. And